Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, welcome back to Physics with Beth and Beth. I'm Beth, and today we are talking about AP Physics 1 Unit 5, which is on torque and rotational dynamics. So in this video, we are diving headfirst into the first word of our little unit, torque. So let's start out with what torque is. Well, the fancy AP Physics 1 definition of what torque is that it's a measurement of the force that causes an object to rotate. That's what I have on the board here. I like to think of it as like how rotatey a force is. That is less fancy and smart sounding, but it gets the point across. So we're talking about how rotatey a force is here. Whenever we talk about force, we often like to have a symbol that we write down because we in physics are often lazy and I don't want to write out a whole 6 letters when I can instead just write one. So the way we often represent torque is with a little squiggly T. This is our symbol. This squiggly T is actually a Greek letter. It is a lowercase Greek letter tau, but it's really just a T with a squiggly top on it. That's all it is. Whenever we're talking about torque, we also need to think about the units of torque. Units are really, really important with physics. We never want to forget them. So the units of torque are newtons times meters. And when I say this, I will often just say Newton meters. Whenever I say Newton meters, I mean newtons times meters, and those are the units of torque. And now, of course, the equation. The way that we calculate torque is with this little equation where we have torque is equal to R times F perp. So this is the little equation that's going to be on your physics sheet, and on your equation sheet in AP Physics 1, and I want to go through this and talk about what each of these two letters mean. So first of all, radius. You guys know what radius is, right? If I have a circle, then the way across it is the diameter and half of that distance is the radius. Well, whenever we talk about radius and torque, I'm not talking about the radius of a shape. I'm talking about the distance between where a force is applied and the axis of rotation. So I'm going to talk a little bit more about that. Here I have like a little makeup compact. My axis of rotation would be my hinge here, and it rotates like this. Okay, so I have an object, it's rotating this way around this axis of rotation. So whenever I push on this, I'm applying a force. So, like so, amazing, magic. Physics is so thrilling, isn't it? The distance that I am from my axis of rotation is what determines this R here. So if I push really close to my hinge here, I can close this, but with some effort because I have a small R, so the force that I'm applying has to be big to achieve the same torque, right? But what if I have a bigger R? What if I have a bigger radius, a bigger distance from the axis of rotation to where I apply my force? Like if I push up here, oh, well, it's a lot easier to apply that torque and to close my little compact thingy here because I have a bigger R. So to have the same torque, if I have a big R, I don't need as much force. So the bigger your radius, the bigger the distance between your force is applied and the axis of rotation, the more torque you have. Think about a door, right? This is why our handles on a door are on the outside of the door, farthest away from the hinge. If you grab a door handle and pull open the door, you're pulling on the side farthest away from the hinge of the door, right? Now, try going up to one of the doors, like get up from your computer or your phone or whatever, just walk up to a door and try pushing on it, right by the hinge. It's really, really hard to close. You have to really push. You get a good workout in from doing that. You have to apply a lot of force to achieve enough torque to close the door if your radius is really, really small. However, if you push where the door handle is, if you have a much larger radius, then it doesn't take you nearly as much force to apply the same amount of torque. Okay, now let's talk about this force now for a minute. Here I wrote force with a little perpendicular sign as a subscript. This is like, remember when we were talking about work? We said that the only forces that do work are forces that are parallel to our direction of movement, right? Whenever we talk about torque, the only forces that do work are forces that are that cause a torque are forces that are perpendicular to our axis of rotation. So going back to my little compact thing here, my axis of rotation is my hinge. My hinge is right here. It is facing outwards towards you guys, right? Pointing out of the screen of your phone or computer. So If I tried to apply a force that was parallel to that axis of rotation, that would be like pushing on the compact this way. That is the silliest way to try and close a compact, right? Like I'm not going to close it by pushing this way. I need to push this way, right? That seems like that seems almost obvious, right? So the way that we write that is we're talking about forces that are perpendicular to our axis of rotation in order to cause a torque. So our axis of rotation is pointing out this way. If I want to cause a torque to close my little compact thing, I need to push perpendicular to that, like so. Amazing. So that is our little equation for torque. So now let's go and do a quick little example. I'm going to draw a really pretty picture. So let's say I had a wrench with a little bolt. So I had a bolt here and I had a wrench. And I was applying different forces on this wrench. So say I had one force that was applied here, and it was 4 newtons. Here, this was 8 newton, or 4 newtons. And I had another force applied right at the end that was 8 newtons. I'm going to say this is point A, B, and C. Which of these forces are causing the most torque on our little wrench and our bolt here? Well, if we remember, the equation for torque is squiggly T is equal to R times F perp. All of our axis of rotation is going to be around the bolt here, and I actually have, this is my wrench. We're rotating around our bolt here. That's our axis of rotation. So all of our forces are perpendicular to that axis, so we're all good on that front. We have 4 newtons applied here, 4 newtons applied here, and 8 newtons applied here. So if I'm just asking you to rank which one is causing the most torque, well, which one is going to do that? Well, it's going to be point C here, right? So torque C is going to be the biggest, both because I have a bigger force here and also because it has the biggest radius. Radius meaning the distance between my axis of rotation and my force. So the radius of C, torque C, is this whole distance, B is only this, and A is only this. So if torque C causes the most torque on my little wrench here, which one causes the least? Well, torque has 2 factors in it. It has radius and force. These two both have the same force, but A has a much smaller radius. So then torque A is the smallest, torque C is the biggest, and torque B is right in the middle. All right, so now let's actually try and calculate one of these. So we're going to keep with the little wrench example because I have a prop and I like to be able to use things like props in these videos. So let's say I have a wrench. It's a pretty big wrench. It's goodness gracious, I can't write. It is 0.25 meters long. And I am applying a force at an angle here. So let's say I'm applying a force right at the very edge of my wrench. And that force is 25 newtons. And I'm applying it, sorry, I've got a little example here, at a 30-degree angle. So I'm applying 25 newtons at a 30-degree angle. I've got my little wrench here, and I'm pushing up on it at an angle. So how do I calculate the torque that is being applied by this force? Well, we are only concerned with the component of this force that is perpendicular to our axis of rotation, right? Well, my axis is here, so I want to break down this force into 2 components, and it is only the component that points straight up that is perpendicular to my axis. So I'm going to break it down. So I have my up component, I'm going to say my y component, and I have my x component. And now all I have to do, or this is also force y over here, is do a little bit of trig to find the y component of my force here. Well, all we have to do is SOHCAHTOA. So SOHCAHTOA, I'm trying to figure out the opposite of my angle, and this is the hypotenuse, so sine 30. So the sine of 30 degrees is going to be equal to force Y, or I might just relabel this as force perp, my force that is perpendicular to my axis, over 25 newtons. So if I'm trying to solve for my perpendicular force, that is just 25 sine 30 is equal to force perp. So if I want to calculate my torque, it is just my radius times my perpendicular force. So my torque is just equal to radius times which is equal to, my radius is 0.25. My perpendicular force is 25 times sine of 30, which if I plug that into my calculator as I did earlier, then we have that my torque is equal to 0.25 times 25 sine 30, which is equal to 3.13 Newton meters. And that is my torque. And that's all we have to do. So all we have to do is break down our force into our different components, identify which component of that is perpendicular to our axis of rotation, and then we're off to the races. And you guys know how to break a vector down into its component parts. You've done that a bajillion times by now. Y'all are masters of that. So that's a concept that you guys are familiar with. Don't get intimidated by it. And then just finding the radius, the distance between where our force is applied and our axis of rotation, which is right here. Okay, now what if I change this problem a little bit? What if I moved my force farther in so that instead of pushing all the way at the end of my wrench, the way I should clarify, that's the whole length. What if instead I was pushing like right here? So instead of having 0.25 meters, I was like 0.18 meters. How would that change the torque? Well, that would just change our value of our radius here. So we're still pushing at the same angle, so our perpendicular force is still the same. We're still pushing just as hard. But now we are pushing closer inward to our axis of rotation, which changes our value of R. So our new torque, I'm going to call that like torque 2 maybe, would just be radius times our force times sine 30. But our radius is now 0.18 meters, which means that our new, if we calculated this out, our force was 25 newtons. If we calculated this out, our torque would decrease to only being 2.25 Newton meters. So that's just a concept that I kind of want you guys to sort of start to get in your head. If my radius decreases, then it's going to be harder to make something rotate-y, right? It's going to be harder to start to cause that turn. Also, what if I push directly on my axis of rotation? What if I continued decreasing my radius all the way until my radius was 0? Well, then my torque would just be 0 times 25 sine 30, right? Which means I would cause no torque. Just like with my little compact here, if I push directly on the hinge, it doesn't matter how hard I push, if I'm pushing on the axis of rotation, I'm not going to be able to cause any torque to happen. So that's the final idea I wanted you guys to be introduced to. All right, well, thank you so much for sticking with me through all that. That was an introduction to torque. Y'all are troopers. Thank you so much for sticking with me, and happy physicsing.